I want to kind of bridge from what you guys just finished. Okay, so yesterday we took a test. What was that over? Proportions. Okay, so the data kind that we are coming from is proportions. And now we're going to do some of the same stuff, but with means. Okay, all right, so what was some of the stuff that we did with proportions? What mainly was happening? Running a hypothesis test, and what else? Making a confidence interval. Okay, so if I said, do you know the average time it takes all Aledo students to get to school? I would be, do you know that number for all the students? Oh, okay, so you're getting into, no, I wasn't blocking. I was just saying average of all of them. Average of all of them, not blocking. Okay, so do we know that? Do we know the population average? Well, if we were to write down, we have a mu, and that represents the population average, which we don't know. Furthermore, if we don't know that, then we would not know how varied those numbers are. What the average distance from the mean is. So we don't know the population standard deviation either. Okay? So that causes problems for us. So much so that we can't use the normal model. Dun dun dun. So if we can't use the normal model, then what are we going to do? All right, I think I might know where we were. All right, so we do not know the population values. So the best we can do is to come up with a what? A what? An estimate, and we'll use a what to make an estimate? A sample. Good. That's where we're headed with this. The fact that we have to use a sample to make our estimate, okay, so what would a sample mean? How would that be notated? Do you remember that? X bar, very good. See, we used to use p hats when we were in the proportion problems, and we're going to use the standard deviation of the X bars to do that. So here's the deal. Here's the first thing that we have, the issue that we come to in this unit. Because we do not have the population information, and this mostly because we don't have this population standard deviation. We can't use the normal model, and we have to use a new type of curve. And that's where we're headed to right now. Oh, we're going to have to use a t-curve. And we're going to run t-tests and get a t-interval. And so here's Mr. T-test himself saying that I pity the fool who doesn't know his population standard deviation. So if you don't know your population standard deviation, you have to do a t-test and t-interval and use the t-curves. So let's talk t-curves. Here we go. So this is on the first page of notes in your packet. Okay, so essentially, again, as most generally the case, in real life, you pretty much don't ever have the real mean, and furthermore, you don't have the real standard deviation. We will have to use the standard deviation of the sample. Because we are using a standard deviation of the sample, we actually will see it sometimes referred to as the standard error. And that is because this standard deviation of the sample is quite a bit more varied, has a lot more variability. Does that make sense that there's more uncertainty in that standard deviation because it's from a sample? Okay. So because we're having to use the standard deviation from a sample, we have more variability. And since we have so much variability, then we have a curve that has more variability than the normal curve. So if we take a look down here, we have a t-curve that it fluctuates more, and it's wider, and it's fatter, and so it has wider tails. Okay, it's still unimodal, symmetric, and bell-shaped, but it will have much wider, fatter tails than the perfect little normal curve that we like to use our calculations on. In fact, I have something here to show you what's going on with that. So here's our little, oh, that's the wrong browser. Sorry, hold on a second. So here is a normal model, but I'm going to show you the t-curve compared to it. So let's take a look at that. Let's see here. Okay, so the red curve is the one that is a t-curve. And it's actually based off the sample sizes. As your sample gets bigger and bigger and gets closer to the population, so watch this, as my sample size is getting bigger and bigger and bigger, then my t-curve will approach looking like the perfect normal curve. And it won't be the perfect normal curve until the sample size is the whole population. Okay? Now, another thing that's kind of interesting to note about this app is, see, it's referencing this percent error here. So this is the percent difference or error that we have different here in those two curves. And so you can see right now it's at 21.19%, so that difference is that. What do you think is going to happen to this percent error as my curve is getting a bigger sample size? Good, it's going to get a smaller percent error. In fact, see, you can see it's at 6% right now, and it's at 3%, at 2%, 1%, and as it gets further up here, the smallest it gets is 0.5%. Percent error difference. You can see a little bit up here difference between the two curves. All right, so in summary, so far, we've talked about how we have to use the sample standard deviation. Because we have to use the sample standard deviation, we have a new curve. It's the t-curved, okay? It is, if n is bigger, then it is not as varied, and it's getting closer to the normal curve. But if n is smaller, then it's much more varied, which that's natural. We've seen that. So as our sample size goes to infinity, or is going to the population, then our t-curve, approaches the normal model. So it will get more and more looking like the normal model as our sample size gets closer to infinity, or the population. Okay, so let's summarize then our t-curves. They are bell-shaped. They have the center still around 0, just like the normal model, symmetric around 0. Every single one of them is different. And what makes them different? There's a whole collection of them. What is making them so different? Okay, the variability and the sample size. Okay, so the sample size that you will come across is going to determine what size standard deviation you have. Phone's making noise. Okay, so our sample size. Now, one last concept before we go on and start doing some actual computing. Okay, there's this thing called degrees of freedom that tells us what t-curve to use. And so I kind of was wondering, well, what the heck is this degrees of freedom, and why do they call it degrees of freedom? And so I went ahead and I was kind of researched that, and I was looking that up. And so what I found out was this. The degrees of freedom come up in many different contexts in statistics. In fact, when I looked it up, I just got all these pictures and all of these videos about robotics and kinematics and a lot of more advanced engineering things. And I was like, well, is this the same degrees of freedom that I'm talking about in my statistics? And I found that it is. Technically, these degrees of freedom are referencing the dimensions that you are dealing with, and it also has to do with the domain of this random vector. So, some physics is involved in coming up with this degrees of freedom. And so I was like, well, that's still kind of weird. I don't really quite understand this. So I watched a video that was a really nice little simple explanation of why it is called degrees of freedom. And so it's about a minute long. I was going to show you that. So let's take a look at this little video here. If I can get that to play. Here we go.
This is an introduction to degrees of freedom. The easiest way to understand the concept is to think about calculating an average, or a mean. Presume that you have 4 scores with a mean of 50. That means that the sum of those 4 scores has to come out to 200. So let's choose our first score. Well, it can be just anything we want. Let's say it's 70. So our running total at the moment is 70. Our second score can be anything we want. We're totally free to choose our second score. So let's say it's a 20, which brings our total to 90. Again, we're totally free to choose our third score, say 45, which brings us up to 135. And at this point, our freedom stops. We cannot have any choice on that last number. It has to be 65 because the sum has to come up to 200. So essentially, when we're doing the average of 4 scores, we have 3 degrees of freedom. If we had 10 scores, we'd have 9 degrees of freedom. We're totally free for the first 9 numbers, but the 10th number is forced on us. In general, when computing an average, if you have n scores, you have n minus 1 degrees of freedom. This same logic carries over when we're doing something like...
And so, you see that connection? That in general, if you have n scores, then you have how many degrees of freedom? Good, n minus 1, because that n minus 1 items can be freely chosen. And they are used to estimate our variability. They are doing that, but that last one is spent achieving that particular mean that you want. So therefore, we know that our degrees of freedom are computed as the sample size minus 1. And the interesting thing is that this is what tells us the specific t-curve to use in calculations. Okay, so because there's infinitely many, I mean, you have a different t-curve formula for every single sample size. And so then we will use this to tell us which curve to look at. And so that will be used to calculate the p-values and the t-values. And luckily our calculator has all of those formulas in its brain so that we can figure all of that out. Okay, so going back to here. So in summary, we got that we're doing means. We've got that we don't know the population standard deviation, so we have to use a sample one. Because of that, we have more variability, and therefore we use t-curves. And then we use this idea of degrees of freedom to tell us which t-distribution to do our computing on. All right, so with that summary in mind, let's go ahead and do our song. And this one is based on Who Let the Dogs Out, and it kind of takes us through the things that we've just talked about. Who's got a mean test? T, 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 not Z. And then this is happening because we are using the sample standard deviation. T, 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 not Z. Who's got a mean test? T, 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 not Z. And because we need to know which t-curve to do the computing on, you must include the DF, the degrees of freedom. All right, so here we go with that.
Who's got a mean test? T, 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 not Z. Sample standard deviation. T, 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 not Z. Who's got a mean test? T, 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 not Z. Must include the DF. T, 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 not Z. Who's got a mean test? T, 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 not sample standard deviation. T, 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 not Z. Who's got a mean test? T, 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 not Z. Must include the DF. T, 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 not Z.
All right, so there you go. Here's the song that you guys refused to sing with me. Okay. Very good. So there are things that we want to remember about our t-test. Now, let's have you guys do a little quick check. I want you to turn to your next page. Which of the following curves has the highest degrees of freedom? And so I'm going to give you a few moments to look at these 3 different curves that you have there and answer those 3 questions, and then we'll come back and talk about that. Okay, so on our, which one has the highest degrees of freedom? How do you know it's 1? Because it has what? Okay, it has the largest sample size, yeah. It would have the largest sample size. 1 has the largest sample size because it is the tallest and the skinniest. Okay, so largest N, so largest degrees of freedom. Very good. Okay, so number 2. Which one has Which one has the largest amount of variation? I think everybody found that one to be 3. Okay, good, because it's the widest and the fattest and stuff. Okay. So now, next is probably the one that people struggled with the most, or at least I got that through the day. Which one has the highest, or I'm sorry, does it say smallest? Critical value. So critical value, what is that? Last chapter, what were our critical values called? Z stars. So this year they are called, or this unit, they are called T stars. Okay? So now that they are on T curves, they're T stars. So if we want a confidence level of 90%, then that means I want 90% in the center. So I have drawn this out for you. You can see on curve 1, I've put 90% of the data here in the middle. So my T curve goes from, my T star, my critical value goes from this location to this right location. Okay, in order to have 90% of the data inside it. Likewise, on the second curve, that's spread out more, the red lines have 90% of the data. So what would you say about the T stars of the red lines compared to the T stars of the blue lines? Which one's bigger? Second one. The red ones are a bigger T star than the blue ones. Good. Likewise, how about our third curve that is most spread out? The T stars are the farthest out. So now, answer the question, which one has the smallest critical values? 1. Very good. So 1 has the smallest critical values. Okay, very good. So that's your basic understanding of those concepts on that. Now, let's get into some actual computing. So if you turn to the next page in the notes, the top part of it asks or gives you some information, I think, about degrees of, there we go, yeah. Degrees of freedom stuff, we've already kind of covered that part. All right, so let's go down here to our hypothesis tests stuff. So for a hypothesis test, we're going to have a T statistic or a T score instead of a Z score. Okay, T scores instead of Z scores. And so those are going to use that same kind of formula. X minus the mean over the standard deviation. X minus the mean over the standard deviation. We just have X bars minus, because that's the sample mean, minus the mean of the population over the standard deviation of the whole sampling distribution. All right. But here is, I'm going to next, really, because we're going to do the interval today and we'll end up doing a test tomorrow. I want to talk to you about the formula right here used for our confidence interval. Okay? In fact, on our formula chart, we have that there. And let's take a look at it. So on our formula chart, the first thing it says is statistic. Last unit, what was the statistic we used with proportions? It was a p hat. But this unit, since it's about means, what will our statistic be? An X bar. Okay? Plus or minus. Last unit, the critical value was a what? A Z star, and we inverse normed to get that. This unit, our critical value will be a T star. Okay? And we'll inverse T to get that. And I'll teach you that shortly. Last unit, our standard deviation was for proportions. So it was that standard deviation, that square root of 1 minus p over n, if we had true p. This unit, remember, for means, it's this. But do we have a population standard deviation? Sigma is a population standard deviation, which we don't have, so we use the next best thing, which is S of x. So our standard deviation is going to be S of x over the square root of n. Okay, so let's first use our calculator and get this critical value. Let's go back and do that, and we're going to practice that here. So let's do that. Here we go. What? Yeah, go get your calculator if you don't have one, because I do want you to practice this. If you have a TI-83 calculator, then your calculator doesn't have this feature. You don't have, yeah, you'll have to use one of my calculators for it. And then, like, to be able to do your home, I think there's a YouTube video that's a program, and I think I have that program on a calculator. I'll look into getting that for you. Okay, so what critical value came from a sample of 15 observations with a probability of 0.025? So 0.025, we're going to go with the fact that it is saying that 0.025 is what is below that critical T-star value. Okay, so how am I going to find that T-star there? How did we find a Z-star when it was looking for it? We did inverse norm, so with this, we're going to inverse T of our one tail, 0.025, but we must include the DF because we have to tell the calculator which T-curve to calculate off of. So we are told here that our sample size is 15. If our sample size is 15, then what's the degrees of freedom? 14. Okay, so this is located in your calculator under second vars. And for me, it's number 4, inverse T. And the area is 0.025 with the degrees of freedom of 14. And do you see how long it takes to think? I mean, look at how long it takes for that to actually compute. Do you know why it takes it so long to compute? Well, it's got to like sort through the curves and find the T-curve number 14 for what, and that formula, and then compute it. It's not like it's the normal curve and it's automatically one particular function. So this is at negative 2.14. Okay? All right. Now, with this next one, it says, what critical value T-star would you use to create a 99% confidence interval? So what is that implying about where 99% is located? If it's a confidence level, or you're making that confidence interval, then where's that 99%? Yeah, the 99% is what is in the middle. So 99% is the confidence level in the middle, which puts 1% split. So there's a half of a percent here, and if there's a half of a percent, it's 0.005 in a tail. I'm assuming then that what this problem wants is both critical values, the positive and the negative one, so I'm going to get one of them. Now, as you go through these, keep in mind, do pay attention consciously. Do they give you the sample size, or are they telling you the degrees of freedom? So you need to keep in mind, do I subtract one or do I not? So let me let you guys finish these up, and then we'll check them. So do that. Okay. So here we already said that this one was negative 2.14. And here we're going to get two values, the positive and the negative, because it wants to, we want to know it on both sides of that confidence level or confidence interval. And was this the 2.86 one? Is that what that was? Okay. Now here on this second one, which one has a probability of 0.05? So to me that means I've got 0.05 down here below it and wants to know that one. So is my critical value going to be positive or negative? Negative, and it becomes negative 2.02. Okay? This next one here says 5% is to the right of what critical value? That means you got this upper 5%. So that's got 95% below it, or you can just know it's the positive version of the one before it. Okay? And then the next one again, like I said, 99% is to the left of what critical value? And so that's your inverse T of 0.99. Okay? Now, I found that we need to know something else that this notes do not have, and so I'm going to be adding those to this next year. But I need to go ahead and have you do this problem with me. So add this problem to your notes down there so that you know how to do this kind. So I want you to find a p-value. That's a probability. That's an area. I want you to find the area to the right of the t-score of 2.01 with a sample size of 27. Okay? So I drew a picture over there to the left. Do you remember how we used to do that with our z-curves? How did we find an area on a curve? What calculator function did we do? We did norm CDF from low z to high z. So guess what you're going to do on these ones? TCDF. So we're going to TCDF this thing. Okay, we're going to do TCDF. And so if I want to do this and I want to go above it, what is the lower t-score that I'm going to be using? 2.01. And what's the upper t-score? Going to infinity, going to 99. Comma, degrees of freedom, because you have to tell it which t-curve to calculate on. So my degrees of freedom would be 26, because I gave you a sample size of 27. And so I want you to go compute that. It's 0.027, is it 5 or 6? 0.02275, okay. 0.0275. So remember what that's telling you is that there's 2.75% of data above this particular t-score, okay? All right, so that's that. That's some basic computing. Now we have one last thing to do, and that is to run a panic model. Go do the whole thing. And so we're going to not do this top section here. So we're going to skip that part and go down here to our last problem that we're going to do for the day. So here we go. On your homework, by the way, I am going to make it such that you just do page 5. We'll do page 6 tomorrow because we're going to hold the test, the hypothesis test for tomorrow. I think it's too much and I want to give y'all some class time to work. So here we go. Andre is a waiter in San Francisco. The Internal Revenue Service is doing an audit on his tax return this year. You know, tax season's coming up. In particular, the IRS wants to know the average amount Andre gets for a tip. In an effort to satisfy the IRS, Andre took a random sample of 8 credit card receipts, each of which indicated his tip. The sample mean is 12.35. So what notation would you use to represent 12.35? X bar, because that's a sample mean, X bar. With a sample standard deviation of 2.25, what's that? S of X is 2.25. Okay. Assuming the distribution of tips is unimodal and symmetric or approximately normal and that all conditions have been met, find a 90% confidence interval for the population mean. Find the for estimating the population mean of all of Andre's tips. So, see, we are using a sample to estimate the population, and that we're not going to do the conditions today or assumptions. We're going to talk about those tomorrow, okay? So, what is the first thing in a panic model? Parameter. What is the parameter here? Okay, it is, first of all, it's not the letter P equals. That was last chapter. Yeah, it's a mu. That's the population mean. We're going to make an inference about the population average of all of Andre's tips. So this unit, we have mu's for our population numbers. And we're going to use that X bar to make an inference about a mu. Okay, so there's our parameter. We will not do the assumptions. The next thing is the name. And so the name is a one sample t-test for means. A one sample t-test for means. Okay. Now, I is calculate the interval. While I let you on the test do the one proportion intervals and tests in the calculator, I want us to keep that understanding the formula and all that stuff intact. So therefore, on these one means, on the interval and the test, I'm going to have you show me the work for those by hand. So let's go and look at this. So the formula, oops. So our formula, you know, that you would write down there for that problem is that. That's your x bar plus or minus your critical value times your standard deviation over the square root of n. Okay, so I want you to fill in your numbers there. So do that. Fill in your numbers. Here's a hint on how to get your t-star. They said be 90% confident, so you got to inverse t to get that t-star. Okay. Okay, so I inverse t to 0.05 comma 7 degrees of freedom. And so my critical value was 1.89. Okay. And then that standard deviation of the statistic, S of x bar, is 2.25 over the square root of n, which is over the square root of 8, so that's 0.8. So there's all my numbers that I'm using, which then gave me this interval here. Let's see. So there's all my numbers I plugged in. 12.35 plus or minus 1.89 times 0.8. After doing all of that, I got that the average of all of Andre's tips, the interval, 90% confidence interval, goes from 10.84 to 13.86. So what's my conclusive statement? What do I conclude then? How do I write that? Good. I am 90% confident that the true average, not proportion. It's so tempting to put proportion because we've been doing that for 3 weeks. The true average of all of Andre's tips is between 10.84 and 13.86. And so then before we finish, and I have you go start on your homework because I want you to do at least the first 5 on that because they're just calculator stuff before you leave today. I want to ask you a question about what we're going to get into tomorrow. The next thing tomorrow says, test the claim that the IRS makes that Andre makes more than $10 per tip on average. So when we run a test tomorrow, what will our null hypothesis be? Mu equals 10. What will the alternative hypothesis be tomorrow? Mu is greater than 10. So the IRS says, hey, Andre, you may think it's 10, but you put 10 on your tax return, but we think it's greater than 10. Based on this confidence interval that you did today, when we run the test tomorrow, what do you think we're going to end up doing? Rejecting the null. Why? Because it's not in the interval. The entire interval is above $10. Since the entire interval is above $10, I think tomorrow when we run our test, we'll reject the null hypothesis and conclude that it is greater than. All right, so what I want you to do for your homework is to come over here to page 5 and only do page 5, which is these top 5 calculator ones. I'll walk around helping you, and then 2 panic models, then you don't have to do the assumptions on them. We'll save the tests on page 6 for tomorrow.